So len will tell me how many items there are in a particular collection, such as a list or a stir. Now, list and stir are also examples of what are called sequences. And a sequence is something that has a sequence of values that you can index starting from 0 up to whatever its length is minus 1. So the len of m here, as we saw, was 6, and so the last item in m is at location len of m minus 1. All right? You can request a subset or a so-called slice of any sequence by using square brackets with colons between some index values. The first value, the first index here, I, is the index to start your slice at. The second index, j, is one past the last index that you're trying to get to. Now we're going to see this pattern of the end of a sequence or the end of a range being specified as one past what you actually want. We're going to see that in many different contexts. And then in addition, we can specify the step size that we want. All right, so here we have ages as a list of ages of people, maybe in a family. So let's say we've got someone that's 3, 12, 5, 33, 68. And we know that ages sub 0 is the first item. Ages sub 4 is actually the fifth item. If I ask for ages sub 0:2, what that means is to give me the slice of ages from item sub 0 up to but not including item sub 2. So that's going to give me a list that's just these two items long, right? The sub 0 item and the sub 1 item, but not the sub 2 item. This is equivalent, what I've just done there, to saying 0:2:1. In other words, what I've done here is I've asked for a step size of 1 in the slice that I've taken from the ages list. As another example here, if I say ages sub 3:5, well, ages sub 3 is actually the fourth item, correct? Sub 5 is actually not a valid index, but it is just one beyond the end of the valid indexes. So it's okay for me to use as the end of a slice. And so 3:5 is going to give me these last two items as a sublist or as a slice. And this again is really equivalent to saying 3:5:1. Whoop, sorry. Now, in this slice notation here, as I've already implied, if the last of the three integers is missing, then the implication is that you want a step size of 1 from your slice. And so, as I already showed here, if I say ages sub 0:2, that's the same as saying ages sub 0:2:1, and what it gets me is everything from sub 0 up to but not including sub 2. If the first index is missing, then the implication is that you want 0 there. So instead of saying ages sub 0 colon 2 to get everything from 0 up to but not including 2, I can equivalently say ages sub colon 2. I don't need the 0. It's implied. And if I leave off the J part here, then the implication is that I want to get a slice that's all the way up to the end of the list. All right, so here's ages, and if I say ages sub 2 colon, well, that means give me all of give me a sub list of ages, give me a slice of ages, starting from item sub 2 all the way up to, okay, this is going to sound odd, all the way up to but not including the item that's too far. Okay, so up to but not including the 6th item in this list of 5 items. Whoop. Okay, so that works fine. The slicing stuff is really handy if you have an enormous data set, an enormous amount of, I don't know, like retail data about a whole bunch of customers, let's say, and you only want to deal with a certain collection of those customers. Then you can ask for a slice of your whole data set that just gives you certain columns, let's say, within the data set. Okay. We can still use plus for concatenation, and we can use star for repetition. If I have this list A containing, all right, this is not very clever, but 0, 1, 2, 3, 4, 5, 6, 7. Yes. Then A sub everything up to 4 gives me 0, 1, 2, 3, and A sub from 4 to the end gives me everything else. So it turns out that for any value, for any integer value, if you say A sub colon, let me do it with 3 this time, A sub colon 2 plus A sub 2 colon, that's really just the same thing as A as a whole. All right, I've got a slice of everything up to but not including 2, and then a slice from 2 to the end, and that gets me that whole list. Or I can swap these in the other order. If I wanted to swap these things around, I could say, give me A sub 4 colon plus A sub colon 4, and that'll give me the same 8 values but swapped, the first 4 with the last 4. Slicing works with strings just as it does with lists. So if I have hello, I can ask for a slice of everything up to but not including the sub 3 item, and add, say, a P and an exclamation mark, and this gives me help as my result. This last one is just kind of silly. If I have S1 containing international, and I say give me from S1 every second character. So I want every other character in this string from the beginning to the end. And what I end up with is itrainal, for whatever purpose that is, and so on. So a list and a stir are both examples of sequences, and sequences can be sliced and moved around and rearranged using plus for concatenation and so on. Any questions about the sequence business or slices? Okay. All right, so it turns out that almost any kind of data in Python, and for that matter, things like functions and classes, are objects. And these objects are stored in memory at some location. Each object is uniquely identified by its object ID. And I can use the function ID to obtain the ID number of any object. All right, so for example, I have A, which is a list. I can ask for the ID of A, and I get some number. I have S1, which is a reference to a stir. I can ask for the ID of S1, and I get some number. I have M sitting around, which is a list. I can ask for the ID of M, and so on. In fact, I can ask for the ID of ID. That's the ID of the ID function. Yeah.
What is the practical use of this?
Of IDs?
Yeah, like, I mean, obviously, generic thing is you can ID everything. You have a unique identification number. But how do people use this?
Yeah, excellent question. So people don't typically use the actual ID number. But what people do want to look at IDs for is to tell whether two different variables refer to the same object. Okay, because if two different objects, if you have two variables and each one of those variables is referring to an object, discover that their IDs are the same, that means that those are actually variables referring to the same object. Okay? So that's what we really care about as far as IDs. Now, depending on what implementation of Python you have, this number that's displayed may be the actual physical memory location where this object is stored. But that's not required. That does happen to be the case for the version of Python that we're using here, that number is actually a memory location. But the weird thing about ID is that there's nothing you can actually do with the ID other than to compare it to some other ID to see whether it's equal or not. Okay. In fact, as I said, even constants like 7, you wouldn't think of the integer value 7 as requiring memory to be allocated in a typical language. But in Python, there is actually memory allocated to contain this 7, and here's the ID of that memory. Okay, if I say, A gets 7, and I ask for the ID of A, I'm going to get the same number. If I say B gets 7, now I have B referring to the same object. So 7 and the variable A, which refers to 7, and the variable B, which refers to 7, all of these things have the same ID. Okay?
Is it fair to assume that every constant has an ID? And if that's the case, there's like a massive number, 1,000 to the 1,000, does that have an ID?
Yes. Excellent. So every object, and this includes integer values, floating point values, string values, lists, every object has an ID. Every object is stored in memory at some location, and so everything has an ID. It appears to be the case that when Python starts up, it sort of pre-allocates memory for a bunch of small integer values. I haven't done any testing to figure out what the range is, but if I look at the ID of 8, well, it happens to be 32 bytes further along in memory from 7, and if I look at the ID of 9, it's 32 bytes further along in memory. So it appears to me that when this implementation of the Python interpreter starts running, it automatically allocates memory for little integers. The same thing is not true for big integers. Actually, let me continue talking about little integers here for a minute. If I say, okay, so I have A referring to 7, B referring to 7. If I say C gets A, well, C gets A doesn't really mean that C refers to the name A. What it means is that C refers to the same object that A refers to. So C is now another variable name referring to 7. Okay, same ID up here. And in fact, I can get kind of creative here. If I say W gets 12 and ask for the ID of W, that's not the same value, correct? But if I now say W minus gets 5, W does now refer to the 7, and the ID of W now is the same as the ID for 7. Okay, so these little integers appear to be pre-allocated, and they don't move around. They're always at the same place each time you run. I don't necessarily mean from one run to the next run to the next run, but within an execution of your Python environment, they seem to be at stationary locations. The same thing is not true for really big integers, because of course you couldn't pre-allocate every possible integer. That would, explode the memory of your machine. So if I say something like J gets 1,000 to the 1,000th power, right? There's, oh, I didn't mean to do multiplication. I'm not sure it's going to matter actually. So here's my ID for J. Now, if I say K gets 1 million, notice that I didn't get the same ID number for J and for K. All right, so in this case, those integer values are not pre-allocated at predefined locations in memory. And so, since they're not in that table, that pre-allocated table for little integers, each time I create a value of 1 million and set up a variable to refer to it, that gets allocated a new ID number. So, questions about this ID stuff and the idea of, all objects, which includes functions, classes, lists, strings, are objects that sit in memory at some location, and you can find out where with the ID function. All right, now if I say M gets a list, 1, 2, 3, and N gets a list, 1, 2, 3, this time it's guaranteed that M and N are not the same object. Okay, when you create a list, that is a new list in its own location, and if you create another list that happens to start out with the same values, it's not the same list. It's in a different location. And the reason this is important, of course, is if I say M dot append 7 N dot pop, well, I don't want appending 7 to M to modify N, and I don't want popping a value from N to modify M. So even though they both started out containing 1, 2, 3, I have modified each of them, and you can see that they're independent of each other. On the other hand, if I make the mistake of saying N gets M, well, now M and N are both referring to the same object, and so if I say N dot insert 0, 14, that does affect what I see when I look at M, because of course N and M are both referring to the same list. Even though I've changed this list a couple of times, it's still the same list at the same location. All right, so that number that I got when I created M in the first place. Okay, so there's the number that I got when I created M in the first place. And that list is still in the same location. Let me just create a comment containing that. Hey. Okay. So when I created M, it was given this particular ID, and now that I have appended a value to M and inserted a value at the beginning of M, it's still the same list in the same location. I've just modified what that list contains, right? Okay. So, we've looked at variables, scalar data types, arithmetic, lists, strings, subscripting and slices, and now we've talked about the idea of IDs. We've talked about the fact that every object has a particular location, and you can find out the ID number. The ID number is going to be unique for each object in your environment. Now we need to know how to compare values to each other and to detect whether a particular value is in a collection or not. Here are the equality, inequality, relational, logical, and membership operators that Python provides. And the precedence hierarchy is pretty simple. From high precedence to low precedence, it turns out that all of the equality and relational and member operators are at the same level of precedence. If you're familiar with Java or C++ or C# or some language like that, this is really going to bother you at first, because what it means is that the less than symbol and the is equal to test have the same precedence. And that's not the case in C or C++ or Java. They're at different levels of precedence. In C, C++, and Java, all the relational operators are at the same precedence as each other, which is higher than the is equal and is not equal. The logical operators, not, and or, are at three independent lower levels of precedence. Here again, if you're familiar with Java or C++, this also is going to drive you nuts, because not all of a sudden has lower precedence than the is equal to test and the less than test and so forth. And that's something that you'll probably make mistakes about that until you get used to Python's rules. Okay. Now, is and is not are comparing IDs, whereas is equal to and is not equal to are comparing values. So, let me show you what I mean. I have A referring to 7, B referring to 7. Certainly A is equal A is equal to B, but it's also true that A is B. That is, A and B are the same objects. They have the same ID. I created J containing the value 1,000,000 and K also containing the value of a million. So j is equal to k, but j is k is false. All right, because in this case, j and k are not referring to the same object. They're just referring to two different objects that happen at this moment to contain the same value. Make sense? Okay.
Sorry, can you repeat that, please?
Yes. Okay. Earlier I said this. I said j gets 1,000 times 1,000. I meant to say exponent. I meant to say 1,000 to the 1,000th power, but I made a typing mistake. And so j now contains the value 1 million. And here is the ID of j. Then I said k gets 1 million. And here is the ID of k. And the IDs are not the same. So the values are the same. J is equal to k in terms of value. But if I ask whether j is k, I get told they're not the same object. They're different objects that at this moment happen to have the same values. Why? Why? You're asking me philosophical questions in a programming class? No, go ahead. I'm sorry.
If 1 million equals 1 million, and up until now we're saying that anything that is ascribed to that 1 million refers to the same object.
No, I didn't say that. I said for small integer values that seem to be true. But for larger integer values, and I'm not sure what the cutoff is, that's definitely not true. It's like when I said m gets the list 1, 2, 3.
So the cutoff is 256.
Pardon me?
The cutoff is 256. What defines the small integer? What are you saying there?
Oh, 256 is the cutoff, you think?
Yeah.
Okay. That's interesting. So let's try that. So let's see. So I1 gets 256. I2 gets 256. ID of I1 is some value. ID of I2 is the same value, but if I say I3 gets 257 and I4 gets 257, ID of I3 and ID of I4 are not the same. Yay! I'm not sure what that's worth, but but the point here is that if you have two variables that refer to the same object, then is will be true. But if you have two variables that refer to different objects, even if they have the same value, is will be false. Okay? Now, a cool thing that you can do in Python that behaves bizarrely in C and C++ is you can meaningfully, let's say I have A is 12, B is 14, 10, C is 8. Well, A is greater than B is certainly true. B is greater than C is certainly true. So I can test whether A is greater than B and B is greater than C, and that's going to be true using my logical AND. But Python is actually smart enough to just let me say, is A greater than B greater than C true? Is that whole relational expression true? And it is. So I don't need in Python to put in the ands and the ors and whatnot in between the components if I'm checking the order of three or more variables. Okay. All right. Well, I think we already looked at examples of is versus is equal to. Everybody okay with equality, inequality, relational, logical, operators? Okay. So next up, now that we know how to compare things, we can start making decisions using if. And the notation for an if in Python starts with the word if, and then some Boolean expression. If that Boolean expression turns out to be true, then the statements in the body or block indented one level within the if are going to be executed. Notice that you need to conclude your Boolean expression with a colon character. Forgetting the colon is a common beginner problem, and it'll sort of drive you nuts. The indentation of the statements in the block is absolutely required. If you forget the indentation, Python is going to scream at you. So here I'm going to say A gets 12, B gets 333, if A is less than 30, colon. All right, so if A is less than 30, notice that the shell is polite here and it indents for me, so I don't have to do anything special in this shell. Let me set B equal to A. Now, when I've started an if decision going, and the statements within the if are indented, how does Python know when I'm done? Well, to tell Python that I'm done, I'll just hit the enter key with no text, and Python will say, oh, I guess this user must be done with the if. And what happened? Well, I didn't cause anything to be displayed, so I didn't see anything on the screen, but A is still 12. B has become 12. All right, because A started out with a value 12, B started out with a value 333, and then because 12 is less than 30, I set B to refer to 12, the same value that A is referring to. Okay, so that's what there is to know about the if test. Everybody good? Whoops, I went up instead of down. All right. I'm sorry?
Is there a nail sparkle?
Yes, there is. In fact, this next example just shows the idea of having more than one statement in the if, and the main thing I'm trying to show here is that notice that they have to be indented at exactly the same level. If the indentation is off at all, even by just one character, Python will yell at you. So right now, A is 12, B is 12, and I can say if A is equal to B, colon, A equals 123, B equals 43, and just because of this accidental extra space that I type, Python says, oh, naughty, naughty, unexpected indent. This is another of my unfavorite things about Python. In fact, it's so bad that if I accidentally hit a space before I start typing, if I say space D equals D gets 123, oh, unexpected indent. So Python is just absolutely ferocious about the indentation, and you have to be consistent. Now, the amount of spaces doesn't matter, but if you start an if and you say, let me just indent by one space, oh, now I've really messed things up. I'm confused. Well, let me indent by 3 more spaces. X equals 12. I have to, whatever alignment, whatever vertical alignment I chose when I started the statements within my if, I have to remain at exactly that same level or Python is going to complain. Okay. So, is this a good thing or a bad thing? Well, there are obviously differences of opinion. This is actually related to the whole business of physical versus logical lines, which to most modern languages, this whole concept of a line meaning anything is kind of ridiculous. You know, in Java or C++, you know, everything's free format. You just type the tokens in the correct order and you're good. But Python, you know, has this very rigid concept of lines, this very rigid concept of indentation of lines, and it does, sort of as a side effect, force every Python programmer to write code that looks pretty much like every other Python programmer's code, right? I mean, you got to indent, so you indent, and your code looks like everybody else's code. One of the bad things about this, though, is that precisely because there is no curly braces used to surround all the statements that are contained within an if you have an if whose body is long, then you know it might not all be able to fit on your screen all at once, and it may be very difficult to figure out. All right, I've got this if up here. Now, where the heck is the end of that if? I don't. You know, it's hard for me to visually keep track of that exact same level of indentation when I'm scrolling up and down on my screen. Of course, people will come back and say, well, you stupid programmer, you shouldn't be writing if statements that are so long anyway, so shame on you. Oh, I knew somebody asked me a question, and I was sure that I was going to answer. Someone asked me, is there an else part to the if? Yes, there's an else part to the if. I thought we were going to get there already, but we'll get there very shortly. Let's continue on. Once you get to the point of making decisions in code, it becomes silly to continue using the shell at this point. We really have to start using an editor to define stored programs so that we can write multiple lines of code in an if decision without having to be so careful about getting our indentation right and so on. So let me launch my idle editor now, which will enable me to write longer decisions and also enable me to write loops and things like that. So I'm going to say File, New File, and later when I'm done writing some code, I'll be able to run that code. So here's my shell, and if I say A gets hello, as we already know. If I could type. So if I say A gets hello and I want to see what the value of A is, I can just say A. The behavior of the shell is that if you give it the name of a variable or some kind of expression that has a value, the shell will tell you what the value of that expression is. That's not the case in a stored program. In a stored program, if I want to see the value of a variable, I need to call a function whose job is to display values of variables. So in this case, in my stored program, after I say that A refers to the string hello, I need to say print A if I want to see anything on my screen. I'm going to say File, Save As, and we'll call this guy example 1. I'm too lazy to type example. I'm just going to call it ex1. All right. So this file is now named ex1.py, and if I say run, my shell restarts the module is executed, and I get the output from the print function call. And now it makes sense for me to start doing more complicated if decisions. So I can say B gets 123, C gets 27. If B is greater than C, D gets 199. Print D. Okay, so now it makes sense for me to type longer sequences of statements. And when I run this, okay, hello is displayed, and then because 123 is greater than 27, the variable D gets created referring to the value 199, and I can print D, and I get the 199 as my output. Now, the idle editor is very simple-minded, and so for teaching, I like to use it because there's no there's no busyness going on the screen here. But you might very much prefer something like Spider or PyCharm or some other more fully featured kind of editing and development environment. That's totally up to you. So far, so good. Okay, now with the print function, I can actually print multiple different values of different types. And the print function will automatically convert each one of these values into a human-readable string representation and display the result onto the screen in this case. Where you type a comma in between the arguments to the print function, what the print function will do at that place is to type a single space character or put a single space character in the output. All right, so I've got, in my stored program, I've got A set to hello, and if I say print A, okay, comma, too many windows, A, comma, Bob, 11/3 and true, 11/3 and true. And now I run this. I'm going to save it by pressing Control S, and then I'm going to run it by pressing F5. And I get out hello and a space, Bob and a space, 11/3 out to 15 good digits and then one garbage digit, and then a space and then true. Okay, so the print function is your friend when you're doing stored programs and you want to see some result be displayed. Make sense? Rather than having spaces come out between the values, it turns out that the print function uses what are called keyword arguments of the form name equals value. And one of the keyword arguments for print is the separator argument, or the separator parameter, sep. And so if I rerun this same print statement, but modify it so that the separator is a comma, now I'll end up getting commas between the output values rather than the default space that usually comes out. Okay, so this print statement printed out the default, which is a space between each output value, and the second one produced a comma between each output value instead. Now the separator is not limited to being a single character. I could say set my separator as space $$ space and have a really elaborate separator. That's fine. So now I've got space, $, space between all the values. Another nice thing to do is so \n stands for a new line character at the end of a string. Come on. If I say I want my separator to be a new line character, now each value is going to come out on a separate line instead of separated by spaces or separated by commas. And as a similar kind of example, anybody know what \t is about? Yeah, \t is a horizontal tab character, right? So now I'll have the values separated by tabs. Okay? Whoops. All right, well here finally we get to the answer of the answer of the question of, can you have an else part? Yes. In a decision, you're required to have one if part, but that's the only thing that's required. Optionally, you're allowed to have as many elif. You're allowed to have as many elif parts as you want, which is just an abbreviation for else if. And then finally, at the end of the whole thing, you're allowed to have optionally one else part. Okay? So I can say things like if b is greater than 300, print b greater than 300, elif 100 is less than b, which is less than or equal to 300, print, well, let's see, 100 less than b less than or equal to 300, else, colon, print none of the above. Doesn't matter. Okay, so there's an example of an if, elif, else kind of sequence, and b was, I think, 123. Yep, b is 123, so I should get this middle print statement executed. And I do. Whoops. Well, yeah, that's correct. I get the value of b instead of the variable name b. But that's what I asked for. It wasn't what I meant to ask for, but it is what I asked for, so that's what I got. One form of loop is the while loop. While some Boolean expression is true, and notice that we again have a colon concluding that while test. While that Boolean expression is true, then all of the statements in the body of the while will be executed. Commonly, you'll have some variable that's initialized to something before the while loop starts, and you typically need to remember to update that looping variable at the bottom of the while loop. If you forget to update the loop variable, you create very easily an infinite loop for yourself. So let's try this out. Well, are you willing to trust me on this one? Okay, yeah. A much more interesting loop and useful loop in Python is the for loop. And the idea here is that we specify some variable name that we just pick out of thin air. The variable name can be legal variable name that we want. And for that variable, set one value at a time to each value in some iterable. Now the iterable could be something like a stir, or it could be something like a list, or it could be some other kind of collection or some other kind of sequence. The variable is going to be set one value at a time to each one of the values in the iterable, and the statements within the for loop will be executed. So in this first case, and this one I am going to just do interactively, I'm saying for I in, whoops, not do, for I in, I'm just going to make up a list of values, 1, 4, 5, 2, 17, colon, print, let's say I squared. Okay, so each of those values in the list, I got 1 squared, I got 4 squared, 5 squared, 2 squared, 17 squared, and the print function automatically adds a new line at the end of each line of output. Make sense? So a list is one kind of iterable. A string is another kind of iterable. Let me print. Now, when you use a for loop to step through the items in a string, Python does not have a separate character type like Java or C++ do. In Python, what you have are one character wide strings, and then strings that are, well, no characters wide, and longer strings. So when you do a for loop to step through a string, the loop variable gets set to each one character wide substring, stepping through the string from left to right. So let me use as my separator a space character. And no, that's not what I want. I don't want a separator. I want my end character. Okay, so print by default displays a new line at the end of each line that it displays. But I don't want that in this case. I want all of these characters to come out on the same line, separated by individual spaces. And so I'm going to set my end character to be a space instead of the default, which is a new line. And there we are. So I have T space, H space, I space, S space, space space, and so on. Make sense? The range function is another iterable in function form rather than as a list or a stir. And the simplest use of range is to just give one argument, and what the range function will do then is to yield values starting from sequential integer values starting from 0 up to but not including whatever n is. So if I say for j in range 5, j is going to take on the values 0, 1, 2, 3, 4, but not 5. Okay, 5 is one too far. On the other hand, if I say for j in range 1, 6, if I give 2 arguments, then the first argument is treated as the starting value, and the second argument is treated as the one too far value. So this way I can get a sequence of values 1 through 5 instead of 0 through 4. And then finally, I can also give a third argument to range. And the third argument we treated as a step size. So here I'm starting at 5. I'm going until I get to or past 100. And I'm going in increments of 7. J. And let me, as my end character, use a space instead of new line. There we go. So I've got starting from 5, stepping by 7, until I would have hit a value that was equal to or greater than 100. All right, so range is enormously handy for stepping through sequential items. You can also use range, because you can specify a negative step, to count downwards, all right, as well as to count upwards. So here I'm saying, let's use a range starting from 4, counting until I hit -1. When I hit -1, I stop. That's one too far. And I'm counting downwards by -1 at a time. So this is going to end up counting 4, 3, 2, 1, 0. Everybody cool with for loops, the idea of iterables, and the range function? All right, so the last thing we need to take a look at here is the idea of modules. So far, everything that we've been using is built into Python itself. So int, float, stir, bool, none, those are all built into Python. List is built into Python, strings are built in, if, elif, else, while, for, range, all of that stuff is built in. If you need to use some facilities that are not directly built into the language, that's going to involve pulling in some kind of module of code. And the way you pull in a module of code is to import that module. One of the most commonly used add-on modules for Python is the math module that gives you this big collection of like 50 math functions. You've got trig functions, power functions, lots of functions. Numerical functions, on and on. My brain is not working. So let's take a look at how we can use some of these things. It's very common for me to want to compute e to the x. And unfortunately, that's not built in. Okay, there is no exp function built in. But if I say import math, now I can say math.exp. All right, because the exp function is one of many, many, many functions that are built into the math module. That's sort of annoying to have to type out the whole module name. So it's very common to import a module as some abbreviated name. And the most common abbreviation that people use for the math module is just plain M. So now I can say m.exp to get e to the x. Okay. I also have m.sine, m.cosine, and I have constants like m.pi and m.e. A whole bunch of things that I get when I import math. If you want a particular function from the math module to be directly available right at the top level, you can say from math import one function like exp. And then you won't have to use any abbreviation in front. You can just say exp1, and there's e to the 1. But I'll still have to say things like m.sine, well, m.sine of, let's say, m.pi over 2. Okay, so to access things other than the exp function, I'll still need to use my abbreviated module name. Make sense? If you want to live really dangerously, you can say from a module import every name that's in the module. This is almost always a really, really bad idea because do you know all of the names for all of the functions and all of the constants that might exist within that math module? What if you had what if you're writing what if you're writing a timber management application and your application has a variable called log and now you import everything from math? Well, log is no longer a log. Log is now a function instead. And this just happens silently. All of the variables that you used to have that happen to have the same names as math stuff all get blown away. You also need to worry about roundoff. If I compute m.exp of the m dot square root of the m dot cosine of m dot pi over 2. All right, well, I have glued into my head from years ago that the cosine of pi over 2 is obviously 0. So, so the square root of 0 should be 0, and e to the 0 should be 1. But I have this cumulative round-off error building up here. And so, well, it's kind of almost 1, but I do have, this carrying round-off problem that I have to always be aware of when I'm doing computations with floating point numbers. And that almost is it. Okay. The last thing that we're going to need to know something about in order to be able to get through the homework is how to read from and create and write to files. Python provides a function named open that you can use either for opening existing text files. You can also use it for binary, but we're not going to do that now. You can use that either for opening existing text files or for creating new text files that you want to write data into. So I'm going to say, let me see, let me import the OS module. So I can say os.dir. Nope. Let me import. Sorry, I always get these confused. Let me import the sys module. So I can say sys.dir. No. os dot d sys dot all right. I'm sorry. Well, get somebody. Okay, get CWD will tell me which directory I'm in. What I'm trying to get is the files that are in the directory. Wait a minute. Maybe it's just os.dir. No. sys.dir. No. All right. Obviously, I don't do that very much. I usually just work right at the prompt level. Okay, so I'm in DFP A1 2019, and I have this program file ex1.py. So let me just work with that. I'm going to say input. Let's see. I'm going to say fin for input file input is open ex1.py. I know that guy's a text file, and I want to read text from that file, and I'm pretty sure that's an ASCII file, so I'm going to say that the encoding is UTF-8. Now, the UTF-8 encoding is the most common encoding for characters throughout the World Wide Web. The ASCII character set is a direct subset of UTF-8. So if I have an ASCII file, it's guaranteed to work. And for larger character sets, UTF-8, you can have multiple, you can have a sequence of UTF-8 characters to create characters from larger character sets. So that's almost always safe. All right, and I was successfully able to open that file. Now, FN, when you open a file for reading, you get an iterable. That thing is an iterable, which means that I can step through it in a for loop and I'm going to get a line at a time. For line. Let me just call it XYZ in FIN. Okay, so if I use FIN as an iterable, I can step through each line in FIN just using a for loop, and I can print out each one of those lines. Okay? And there we go. There's the contents of that ex1.py program file. Anybody notice anything that looks a little fishy here? Sorry? I've got a bunch of blank lines in here. It seems like everything is double spaced, right? And the reason for that is that when I read a line from FIN, the string that is stored into XYZ includes the terminating new line character at the end. So when I print that line, I print the characters in the line and the new line character and a new line character, because the print function automatically adds another new line character. All right, well, once I have read from a file, I can do what's called rewinding the file to go back to the beginning, but it's just as easy to say fin.close and reopen the file again. So let me reopen that file again. All right. And this time when I say for line in FIN, how could I get rid of the last character in the line? What's the index of the last character in the line? -1. That sounds good. So let me change line to line up to but not including -1. And then print the resulting line. Make sense? And now I'll get that file single-spaced. All right, so that looks better. Rather than displaying this stuff on the screen, if I wanted to store this into a file instead, I could also open an output file by using the WT notation, meaning that I want to write text to the file as opposed to read text from the file, which is what I get with RT. So I'm going to open a file for writing text using the same encoding, because I at least here am just dealing with ASCII characters. And rather than the print function, I can say fout.write, and that will simply write out to the file whatever was read in. Now, in this case, the write function does not automatically add a new line character, which is why when I'm doing this loop saying, while I'm getting lines from fin, write them to fout, I'm not stripping off that new line character at the end because I want that new line character at the end of each line to be written out to the output file. And this trivial little bit of code here is code that will make a copy of a file. And making a copy of a file is the first step in being able to do arbitrarily complicated processing of an input file to create a different output file based on that input. Any questions? Cool, we're a minute early. Okay, if you do have any questions about anything, like I said, I'm always on email, at least for another 12 minutes. I'll be on email this evening. And if not, I'll look at it in the morning. And, feel free to ask me questions. I am going, as soon as this course is over, I'm going to, well, let's see now. Your first homework is actually reading and experimenting. Normally what I like to do is to divide everybody up into teams. Yeah, I'm going to do that anyway. So, you'll go through your homework, and then what I want you to do is to compare what you did with a partner to see whether you had different interpretations of something or different approaches to doing something. And then one of the two of you can turn in the Jupyter notebook that you agree that you want to represent your work. Okie doke. So we're all set, and I will see you next week.